All right, guys, it's been a while since I did a an online lesson video, but I guess that's going to be required for now. Um, so I'm going to just show you what today's lesson is going to entail. We're going to talk about what light is and the electromagnetic spectrum. Let's move this back down. I'm definitely going to be a little rusty with this, but that's okay. So today, essentially, you're going to be learning know what light is, how it's created, and the different parts of the electromagnetic spectrum. You're going to watch this lesson video, take notes like it's a normal PowerPoint because this is the start of the new unit, and you're going to get tested on this eventually. As a part of it, you're going to watch all the episodes of the electromagnetic spectrum tour and fill in the chart from the PowerPoint, and I'll tell you a little bit more about that when we get there. Your classwork and homework, I want you to read section 11.1, which goes over a lot of the stuff that this lesson covers. And then I want you to try and complete on page 469, number 1 to 9, and I'll revisit this at the end of the video. So let's see if I can get my PowerPoint up and running. Here we go. And I'm going to start the slideshow. So our new unit is light and optics. Let's just make sure my writing tool works. That's good. And get into, and like through this video, you'll probably have to pause this a bunch of times because I'm not waiting for you guys to write things down. So you guys pause it as necessary. So first slide, what is light? Well, light is a wave of two different types of fields, electric and magnetic fields. And its properties depend on the frequency and the wavelength of that light wave. So light is a wave. Now it's different than a water wave, but it is still a wave. Water waves, sound waves, they all are similar things. And the frequency and the wavelength can be calculated using the wave equation C equals F times lambda. Now back to this first statement here, that it's a wave of electric and magnetic fields. It actually would look something like this if you were to graph it. Whereas one of these waves, let's say this one right here in the blue, would be the electric field. And then the one that's going side to side is the magnetic field. And me writing over top of that makes it look a little uglier, but that's what an electromagnetic wave is. So the light that you can see, the light that's coming from the light bulbs, the light that's coming from the screen you're looking at, and the light that's filling the room right now is all these waves of electricity and magnetism. They just vibrate really, really fast because that's what makes a wave. And so like it's times 10 to the power of 14, if you understand scientific notation, times per second. So C happens to be the speed of light in this little equation, and its value is 300 million meters per second. Did I get that right? I need 8 zeros. 2, 4, 6, 8. Yeah, I did. Meters per second. F is the frequency of the wave, and frequency is measured in hertz, symbol Hz, and the wavelength, or this funny symbol here, is lambda. It's like an upside down Y, and it stands for wavelength. And it's literally just the length of these waves from crest to crest here, like top to top. And you can measure it from any top to any adjacent top. So that would be the wavelength, and that would be the wavelength there. So you measure that, its standard international unit is just meters. So you've got speed of light in meters per second, frequency in hertz, and the wavelength in meters. Now, if we ever have to use this formula, if you like a little triangle, this could be worth writing down. I'm going to make that a little nicer. It's C, F, and lambda. You can pause it at this point if you need to catch up, otherwise I'm moving on. The type of electromagnetic wave depends on how fast the electric field wiggles. How fast it wiggles is kind of a goofy way of saying the frequency. And here are the main types of electromagnetic waves. Starting on the right, well, it goes from shortest on the left. See, it says wavelength here in meters. So the shortest waves, I'll just write over here, these are short. And then these ones over here are long. Now, if you know your scientific notation, you'll just see that wavelength times 10 to the negative 14. And on the right side, we've got wavelengths of 10 to the power of 4. So the long ones are on the right and the short ones are on the left. But I'm actually going to go and start with visible light. Now, visible light is just this little tiny patch right here. And this diagram spreads it out so you can see what the colors are and what their wavelengths are. These are nanometers. Nanometers means times 10 to the negative 9 meters. So 400 nanometers is your violet light. 500 nanometers, you're getting into the greens. At 600 nanometers, you're changing from green to yellow, almost into red. And then by the time you get to 650 and then to 700 nanometers, you're into the red. And then just above red that you can't see, going back to the top here, we have infrared radiation. So that would be right here, right after the visible spectrum. So let's go that way. Let's go from the visible light and up, or to the right, so longer waves. So infrared rays are just a little bit longer than what our eyes can see, okay? And they would fall in that next spot. Just a little bit longer than that, we get our radio waves, which are, well, from here to here. These are all types of radio waves. Radar, FM radio, TV signals, shortwave radio, and AM stations. Those are all types of radio waves. And they are the longest types of electromagnetic waves. Now, if we look on the other side, just below what we can see in terms of wavelength is on this side, so just a little bit shorter wavelength than violet is your ultraviolet radiation. Now, ultraviolet, as you know, can burn your skin. It doesn't go through your skin. It doesn't get to your bones or anything like that, but it can burn your skin pretty badly, as I'm sure some of you know. And it's just a little shorter wavelength than we can see. After ultraviolet, a little shorter than that is X-rays. And X-rays, they can go right through our skin and they get reflected off of our bones. That's why it's good for using in medical imaging to see if you have a break in the bones, because they'll go right through all your soft tissues and just reflect back to the screen when it hits something hard and dense like bone. And then if we go even a little shorter, well, not a little shorter, a lot shorter than that, we get to gamma rays. Gamma ray radiation will go through, it'll go through basically all of it. It'll go through your bones. It'll go through everything. It's actually quite dangerous, gamma ray radiation. They turn the Hulk into the Hulk if you're into that sort of thing. And gamma rays cause cellular mutations. They can do a lot of cellular damage, and long-term exposure to gamma rays would almost certainly result in death. So it's a decent diagram, but I don't know if you can tell by my descriptions, but I'm just going to erase some of the stuff that I wrote so you can go back if you wanted to include any of that. But I'm just going to include that on the right side, radio signals and infrared light and visible light, they're actually low energy. They don't hurt us. AM and FM radio signals, they don't hurt us. They don't go through our skin. They don't scramble our brain or anything like that. And short wavelength um, electromagnetic waves, they are high energy, meaning they can damage us. They can do things. Ultraviolet, X-rays, and gamma rays, they can do stuff. All right. So, and then we're kind of in the middle. By we, I mean the light that we can see, visible light. It doesn't really do any damage to us. Really bright visible light, I suppose, could damage your retina if you stared directly at it for too long. The sun, believe it or not, sends out a full spectrum, so it sends out pretty well well, it's not quite a full spectrum, but it sends out most of these wavelengths of light. So it sends out gamma, X ray, radio waves, and of course, visible light. That's how we can see it. Um, Anyways, that's something we'll get into a little bit more later. So, like I said, you can drag this video forwards, backwards, pause it, write down things that you think you need, and so on and so forth. So, the next part of this lesson involves you pausing this, really, and filling in all of these types of radiation that are covered in this video on the electromagnetic spectrum. The link is here, but I also included the link on Google Classroom. So just click that and it takes you immediately to episode 1. And if you just watch each part, now the whole thing's like 30 minutes long, so it takes a while to go through, but each part is only a few minutes long. I believe it starts with radio waves. And then you talk about, okay, well, what wavelengths are radio waves? It'll tell you in that video. What types of things make radio waves? So, radios, TV transmitters, stuff like that. But it'll give you good examples in there. You just watch for them and write them in there. And then applications or effects. So any other facts, really, this is kind of a catch-all column here for anything that they can be used for, or what sort of effects they can have on things like the human body in that. And you may have a little bit of crossover from that column and that column, right? I really just want you to have a nice note in this table on properties of these different types of radiation. You should have all those types I very briefly discussed on the last slide. You should have a spot for each of those here. Okay. And maybe I will actually show you that link right now. Let's just take a look at it. All right, let's not click it here then. Let's just get out of the slideshow for a minute. I'm going to discard that, bring this up, go over here, and I'm going to click our video link. And there it is there. It'll bring up episode 1. If you pop it up in the YouTube app, then it will get you to all the other episodes as well. All right, it's just called Tour of the EMS. That stands for Electromagnetic Spectrum, and episode 1 is right there. All right, moving on back to this. So you can stop listening to me right now and go and do that. Fill this table in as best you can, and then come back to this video when you're done. Because the next part of this is on sources of light. All right, so things are luminous if they give off their own light. For example, a candle is luminous because it gives off light. You and I, we are not luminous because we don't give off light, we reflect light. In a dark room, we don't look like anything. The reason that we see each other is that light in the room reflects off us and comes into our eyes so that we can see things. So just to end this intro lesson, I'm just going to talk about the different types of luminosity, different sources of light. Starting with the first one, incandescence. You may have or may not have heard of an incandescent light bulb. It's light given off due to a high temperature. So old school light bulbs do this. Old school light bulbs have a little wire in them called a filament. And when electricity flows through that filament, it gets very hot, so hot that it gives off light. And that's called incandescence. Just like before, pause this to write down the definitions for each of these, and then we'll get to the end of this. And there's a picture of that old school light bulb getting so hot that it glows. Number 2, Fluorescence. And fluorescents are chemicals that give off light immediately when they're hit by ultraviolet rays. So things like glow in the dark paint and stuff like that, when the sun's light hits them, which does have ultraviolet rays in them, they will glow. Now, for fluorescents, as soon as the ultraviolet light is taken away, they also stop glowing. So this isn't like glow in the dark stickers and glow in the dark t shirts, because they keep giving off light after the UV rays are taken away, after the ultraviolet rays are taken away. A better example of these are fluorescent tubes, fluorescent light bulbs. And you see these throughout the school. And what happens in those is, well, there's a transformer that's connected to them that makes the voltage jump to about 600 or so volts. And that causes some ultraviolet rays to go through those tubes and cause them to glow. There's a chemical in them that glows, causes fluorescence. Phosphorescence, now this is more your glow in the dark. And now these are chemicals that give off light when hit by UV rays. Now all of a sudden that sounds the exact same as the last one, but here's the key: they stay luminous for long periods of time. So now this is your glow in the dark stickers, your glow in the dark t-shirts. So these things, you usually charge them up, so to speak, when you take them out into the sun, because of course the sun does give off ultraviolet rays. That's what burns your skin. So if you have a t-shirt that's glow in the dark, it needs to be exposed to the sun for a period of time, and then it stays luminous for a long period of time. Glows in the dark. Next is chemiluminescent, and these are chemical reactions that give off light. And some living things will also produce the chemicals, and it's called then bioluminescence instead of chemiluminescence. Where you have seen this probably is like glow sticks. I don't know if you've ever used a glow stick before. Most people have. You'll notice that you have to crack them to get them to glow. You're not really cracking the glow stick. What you're doing is you've got a plastic tube on the outside with a chemical in it, and then you've got a glass tube on the inside with another chemical in it. So when you crack it, when you bend it, you break the glass that's inside. The two chemicals mix, and it starts to glow for a long period of time. And of course, fireflies are a good example of bioluminescence. It's the same idea. Two chemicals mix that cause light to be given off, but it happens to happen in a living thing. Almost to the end here, triboluminescence. Now, I've had varying degrees of success doing this myself, but if you have access to like those wintergreen, oh shoot, what are they called? Wintergreen, some sort of breath mints. The name eludes me now all of a sudden, but I used to have some of those. So anyway, they have crystals in them that when are scratched, crushed, rubbed, then some light can be given off. And I've tried this and was successful on my own at home before, just kind of biting into these wintergreen mints, just with the lights off in the bathroom, looking in the mirror. So certain crystals will give off light when they're disturbed, scratched, crushed, rubbed. And you can, if you have access to these things, you can try that at home if you want. And I think we're just about at the end here. Electric discharge. Electricity flowing through a gas can cause the gas to glow, and different gases glow at different colors. So if you get a large enough current to flow through the air, then you're going to get it to glow like in a lightning bolt. And if I get a chance to, when I'm in class, I will show you some other gas discharge tubes just to show you the different light that can be made by just putting high voltage, or high current, I should say, electricity through them. Actually, it'd be high voltage. It's the energy that matters. Just let me make sure we're almost to the end here. Yeah, we are. LEDs stand for light emitting diodes. Lots of our lights, especially Christmas lights, even the tubes in the ceiling in the classroom, they look like old school fluorescent light tubes, but they've actually been replaced with LED tubes. And they're made of little crystals of silicon that light up when electricity flows through them in the proper direction. Now, that's not that important that you know for this course. That's really an electricity problem. but they do have to flow the correct way. Now, the reason that you see a lot of light bulbs being sold as LEDs now is they don't waste energy as heat. Light bulbs that are incandescent light bulbs, that's that first one I showed you, they actually use about 95% of the electricity just to heat up. And then 5% of the energy is actually converted to light up your house or your room or whatever. So it's 95% waste, you could say. Whereas LEDs don't produce any heat, and therefore they're producing, it's not 100%, but it's darn close. They also don't use mercury. Mercury is used in fluorescent tubes as one of the mercury vapor is used in there. And they also last a long time. They last a long time because they don't heat up. Incandescent light bulbs eventually burn out. I'm sure you've heard of that before. So, eventually that filament is just burning for so long that it just burns out. It breaks. If you look inside a light bulb that's burnt out, you'll see that filament is actually broken and burnt. And for that reason, LEDs last a long time. So it's a good technology. It's not perfect. I've had LEDs fail on me, but they're pretty good. And then finally, lasers. You don't actually have to go over any of this. You're going to read about it on, I think, Thursday, anyways. But we'll look at this. Lasers are a very powerful light source, and just some pros, not even pros, properties really of lasers is that the light is very intense, meaning very bright. It's all exactly the same color. So you're not using any sort of like color filter or anything like that. Like a red laser is all red. And the beam of light stays together longer as a beam. Whereas, like most light sources, they all spread out in like a sphere, right? So the energy is reduced the further you get away. Whereas a laser beam, it all stays together and goes in a line, like in a laser pointer. And when I get back, I've got little demonstrations of all this stuff that I can show you if you guys remind me, especially. Okay, so that concludes the first part of uh, of our lessons on intro to light and what it is and stuff like that. Make sure you do take the time to write down the notes. Like I said, you don't have to look at the uses of lasers. That's something you guys are going to look up on your own, anyways. Let me get out of this PowerPoint for now. I don't need any of my notations. I didn't write anything particularly interesting on it. And like I said, what I want you to do next is I want you to read through section 11.1. It's just the basics of what light is. It talks about the electromagnetic spectrum again. And I want you to try and answer questions 1 to 9 on page 469. Now, the homework that I'm assigning for tomorrow is also the same thing, at least for the questions, page 469, 1 to 9. So if you don't quite get the questions done today, don't worry about that. I don't have additional questions to assign tomorrow. You're just going to continue with those questions. So even if you just get section 11.1 read and you get a start on the questions, that's probably fine for now. And then tomorrow you can finish off the questions. All right. I think if I can remember how to end the recording, then I'm going to do that now. All right. That's all for now. Make sure you email me if you have any questions. I should be by a computer for most of the day.